Welcome everyone. In today's lecture we will discuss an alternative formulation of transformer. Okay, and this is a very new development. I would say 1 year of development, recent development, which is basically the premise behind the recent interpretability work that we are going to discuss in the next lecture or next to next lecture. Okay, so in this lecture we will discuss how we can dive deeper into different components of a transformer model and understand it in a very different point of view. Okay, let's again go back to the self attention, mask self attention that we discussed long time back. Okay, mask self attention, what was it? If you remember, we essentially compute an attention score. Attention score is what? I mean, you have these hidden states, let's say at as a specific layer L minus 1, right? So what you do here essentially is that you for every hidden state, right, you have now these hidden states correspond to different inputs, right? Let's say input x1, input x2, x3 dot dot dot. So we have 3 weight matrices, one corresponding to query, other corresponding to key, other corresponding to value, right? And you obtain 3 different representations for every token. And now each of these representations will be used in different ways. For example, let's say when you take the dot product between a query and the key vectors of other inputs, right, this dot product, you take the dot product and then you get the attention score. From attention score you get the distribution using softmax, right? Here as you see, this is basically a normalized dot product, and then the attention distribution will be used for a weighted sum, right, over the value vectors. Okay, so this is normal scaled dot product attention. The problem in the in this dot product is that at every token, if you look at a single token, it can now attend to all the tokens, right? Tokens can appear before the current token, tokens can appear after the current token. So you cannot use this this kind of self attention layer in a decoder only model or a decoder layer, right? So for that, what you need a mask self attention, right? In mask self attention, what we do, we essentially, if you think of this matrix as a attention score matrix, right, you have these numbers, right? Okay, so what you do, you essentially mask the upper diagonal part of this matrix, right? And how do we do that? We add a mask matrix called M, and so essentially those numbers which fall above the diagonal will be masked as minus infinity, because then when you take softmax, this minus infinity will lead to 0. This we already discussed. Okay, mask self attention in decoders. Now once we have this mask self attention, what's the next operation? The next operation is feed forward. In the feed forward network, there are essentially two projections. The first one is kind of an up projection, and second one is down projection. You have 2 matrices, right? So these are essentially the operations, the main operations: self attention, feed forward, and then this residual connection. Now let's dive deeper into this one, and let's look at only one token. This is a token level perspective of transformer, individual token. Forget about multiple tokens, just focus on only one token, right? Let's say the ith token. I think I already mentioned in this perspective, residual stream perspective, what we consider all these operations like self attention, multi-headed self attention, right, feed forward. These are just an additive operations over the vector, right? So you think of a stream. This is a stream or a pipeline, right, where the input to this pipeline is the word itself, right? And at every layer you essentially add something to this stream, right? And what are the things that we are adding? We are adding attention score, and we are adding feed forward network score, MLP score, right? And if you have multiple heads in the attention, so you will essentially add multiple things to the stream. Okay, so this is the token. You get the embedding. Now at every layer L you have different heads, right? Multiple heads. These heads will essentially contribute separately, right? They will basically be added to the stream. This is the stream, and you will get an intermediate representation after attention. This we call as x mid, xi mid, right? And then we have a multi-layer perceptron feed forward network. This will produce another the output of this will basically be added to the stream. Okay, and we keep on doing this thing for capital number of layers, right? And at the end, if the task is to produce the next word, let's say this is a decoder only model, produce the next word, what you do, you pass the last hidden state through another layer which we call as unembedding layer, right? Embedding and unembedding. Embedding layer is at the beginning, which embeds a token to an embedding space, which basically converts a dictionary word or a vocabulary word to a representation space, and the unembedding layer converts the representation space to a dictionary word. Okay, it's called unembedding layer, and here the unembedding layer is denoted by W sub U. So this is called the residual stream perspective of transformer. Okay, so let's dive deeper into these operations very carefully, right? And what is important here is the dimension, so we need to take care of the dimension very carefully. So let's assume that you have tokens, right? T1, T2 ... Tn. Okay, and so these are tokens, and from these tokens you obtain the embeddings, right? x1, x2 ... xn. Okay, and how did you get it? You basically got it through this embedding layer WE. Okay, now you can think of a matrix X which represents the input x1, x2 ... xn, right? What is the dimension of all these xi's, right? The dimension of all these xi's is essentially D. And what is the dimension of X? X is a matrix, right, where all this n number of all these n inputs are stacked one after another. So the dimension of X is essentially n cross D. You have n rows and each of the dimension is D. Okay, let us denote another let us use this notation XL. Now remember, this X matrix gets updated after every layer, right? In the residual stream view, your input is the X matrix. This will be processed through attention, this will be processed through feed forward network, and things will be added to the actual residual stream. So X will be added, X will be updated after every layer. So for every layer L, we have this X matrix which will be updated, right? So one of the elements of this X matrix is, let's say, xi. This is the ith token, ith word at the lth layer, right? This is ith, remember this, ith word or ith token at lth layer. Okay, and remember, when we compute the attention, mask attention at the ith position, right, I will only consider those tokens which appear before I, right? So x l I less than equals to I, sub less than equals to I, this is what? This is essentially a matrix which has all those representations of tokens which appear before I stacked one upon another, right? So what is the size of this matrix? I cross D. This is essentially a subset of XL, which is N cross D. Okay, now this notation is important because this will be used to calculate attention. All right, so now we look at the attention block carefully. Attention block. So attention block. So in attention there are essentially three operations. The first operation is query key dot product. The second operation is whatever you obtain, that will be multiplied with the value, right? The third operation is whatever you obtain, that will be projected through another layer for adjusting the dimension, right? Because remember, this is multi-headed attention. For every head, what is the head, by the way? Let's say this is attention, right, at ith position, right? There are multiple such heads, right? And the dimension of these heads can be different, right? The original dimension is D, and let's say the dimension of this head, individual head, is denoted by H, right? For example, for the first head, the dimension is, let's say, 4. The second head, the dimension is 10. The third head, the dimension is 20. Generally, we use same dimensions for the heads, which may not be same as D, right? So H may not be same as D. Okay. So after attention score, attention output, we need to project it back to D. Otherwise, this will not be added to the residual stream, because in the residual stream, the dimension is always D, isn't it? So let's compute the attention weight. Attention weight for the token I at the Lth layer for the Hth head. Let's focus on only one head H. Right? Let's assume there is only one head H. Okay, Lth layer, ith token. Please visualize this. Okay, otherwise it would be difficult to compute. So what is this attention weight? The attention weight is after the score after query key dot product, before the value dot product. Okay, this is after query key dot product. So at the ith token, the representation is xi, right? Xi, but this is Lth layer. So how do you get the, so all these operations are happening at the Lth layer. What is the input to this layer? xil minus 1. So xil minus 1 is the input. From here I will generate all the query keys, whatever, right? So xil minus 1 will be multiplied with this query matrix, right, at Lth layer H head, right? This will produce what? This will produce the query, isn't it? Then how do you get the key? So to obtain the key, now there are, so how many keys are there for this query I? I number of keys, right? And this matrix will be used here, of course, for L minus 1th layer, right? So x L minus 1 less than equals to I, right? This is the input for calculating the key, and I should also have a key matrix, right? LH. Okay. All right, now let's look at the dimension, and based on that we will decide whether I need a transpose or not. Here I need a transpose, I'm telling you. Okay, so let's look at the dimension first, then you will realize. So so the dimension of this guy is 1 times D. What is the dimension of this one, this is D times DH. What is DH? DH is the size of the head. So the H that I mentioned, right? This is basically DH. DH is not same as D. Okay, clear? What is the dimension of this? This is I cross D. What is the dimension of this? D cross DH. Okay, so from I cross D and D cross DH, I will get I cross DH. Okay, and this will be transposed, so I'll get DH cross I, right? And here I have 1 cross DH, right? And 1 cross DH and DH cross I will be multiplied, will get 1 cross I. What is 1 cross I? 1 cross I is basically a vector corresponding to I number of previous tokens, and these are attention scores. So we are good so far. Okay, so now if we modify this little bit, if we just unfold the transpose WQ L comma H WK L comma H transpose X L minus 1 transpose. Okay, this you see that there are essentially two matrices which are getting multiplied, and this is called, this we denote by a single matrix, right, which is WQK, right, at the lth layer. Okay, H head WQ WK transpose, right, and we call this as query key circuit. Now, why suddenly circuit is a fancy term? I also don't understand why these fancy terms are being used, but essentially you think of it as neural networks, where, I mean, these are basically what? These are two matrices, two fully connected matrices, right? I mean, layers where all the neurons are connected to each other. You can think of them as basically neurons which are connected, and I mean, you can just assume this is a circuit. Like electrical people would love this terminology, love or hate, I don't know. Okay, so this is called query key circuit. So this is just attention score. So this attention score will be passed through softmax. Okay, which will give a distribution, and this is the weighted distribution, weighted average. There's softmax here. Now I move from attention score to actual attention vector. For that, what I need to do, I will take this one and then I need to multiply this with the value, right? So now look at here, AI, right? LH is okay. AI is essentially a vector. So each of these elements can be denoted by AI comma J, where J ranges from 1 to I. Okay, so to calculate the actual attention vector, let us write in this way: J, which is less than equals to I, AI comma J LH, this is the attention score, right? This will be multiplied with what? This will be multiplied with the value, right? How do you get the value? So for ith word you are calculating the value, or the value will come from J. Query has already come from I, right? Keys and values will come from J. So the input for this will be J L minus 1, and I need a value matrix WV LH, right? This will give you the output. Now see this, what is the dimension of this this part so far? So So this is a scalar, isn't it? Aij is a scalar. What is the dimension of this? This is D. What is the dimension of this? This is D cross DH, right? So this will produce what? This will produce a this is 1 cross D, 1 cross DH, 1 cross DH vector. But in the residual stream the size is D, the size should be D. So I need to again project it to D. So for that I need another matrix which will be multiplied here, which we call as output matrix, OWO L comma H. What is the dimension of this? The dimension is DH times D. So this will produce 1 cross D, right? So and this we denote by, so this is my attention vector, okay? This I denote by ATTN, lth layer hth head, right? X L minus 1 is the input, yeah, okay? So for a single attention head H, I will get a vector of size D. There are H number of such attention heads, right? And each of them will produce a vector of size D. How do we combine them? If we concatenate them, then the size will be D times H. We can't concatenate them, we can add them, right? So we could have concatenated if we had not used this output matrix. Let's say if we had let's see if I had produced a vector of size DH, right? And let's say there are H number of such attention heads. If we concatenate them, let's say H times DH should be equals to D. But we did not do it in here. For every attention head will produce a vector of size D. There are H number of such attention heads, those will be added. Now, so this is for a specific head H. So for the final attention ATTN L at the lth layer, input is the same, XL minus 1 less than equals to I. This will be simply the sum H equals to 1 to capital H, right? Attention L comma H, right? This one, X L minus 1, clear? This will produce a vector of size D, okay? Now this attention vector will be added to the residual stream, and in the residual stream there is already this vector X I L minus 1 which is coming in, right? So through this residual connection, right, this will be added. So this plus X L minus 1 I, these two things will be added, and this will produce what? This will produce the output for the feed forward network layer. This will produce the input for the feed forward layer block, right? So I call it as Xi mid, right, layer L. So layer L is not done yet, okay? Let me go back to the picture again. Here, look at here. So far I have calculated this one, Xi mid L, right? I have calculated the heads, added them, and I produced this one. I'm at this position, right? Now what I need to do, now I need to pass it through MLP, right? So this will be passed through an MLP which is denoted by M here. M is a function which again will segregate later, and this will be added with this, and this will produce the output after the MLP, which we denote as XIL, okay? Now let's focus on this MLP layer M. So we have seen two things in attention, right? One is called the query key circuit, right? What is the query key circuit? Query key circuit will look like this, okay? WQK LH, right? There is another circuit which was created here. If you look at this equation again, you see there are two matrices which are getting multiplied. right? We call this output value circuit. Output O, value V, output value circuit. Okay, and we denote it by WOV LH, which is WV LH WO LH. Okay, output value circuit. So output value circuit is responsible for writing things to the residual connection, residual stream. To the output value circuit, you compute this attention, and this will be added to the residual stream. Now later on we will use this output value circuit extensively. Remember this notation. So in feed forward layer, as we know, there are two projections, right? So one is this matrix, which we call W in, which will project it to one dimension, and this will again down project it to another dimension. This is through this weight matrix W O out. Okay. Now let's look at this equation here. Xi mid L. What is this? This is the output of the attention. Right? This is the output of the attention which you obtained from the previous layer, from the previous computation. This is fed to W in L, the first projection layer, right? And then we have some nonlinearity, a normal MLP nonlinearity, right? This will further be fed through W out, right? And this will produce the feed forward output. And this feed forward output, FFN output, will be added to the input through residual connection, and this will produce the output for the residual stream. Although this looks like a very simple operation, but if you look at it very carefully, there are very interesting observations that you can infer out of this equation. So what is again, let's focus on the dimension, right? W in L, please pay attention to this notation. Okay, W in L is this matrix, right? What is the dimension of this? The dimension of the input Xi, the dimension is 1 times D, the D dimension, right? What is the dimension of this matrix? D times, it will project it to a some dimension, right? The dimension here, let's call it as DF. Okay, so what is the resultant dimension? Resultant dimension is 1 cross DF, right? What is the dimension of this D out? The dimension is DF times D. If you look at it very carefully, what is actually happening here is, I mean, we can interpret it in this way. This is this W in matrix, forget about the layer, W in matrix, where there are DF number of columns, isn't it? DF number of columns, okay, and you are multiplying this with a vector Xi. So what is going to happen? So when you multiply this, it will essentially act like some sort of pattern detector, right? So it will, so depending on this input, it will essentially retrieve some sort of pattern out of this X in, W in, and we call this matrix the key matrix. Now this key and the previous keys are different. This is not the query key value. This is a key matrix that we discussed in the Rome paper, right? Key value memory. Okay, as if there is a key which is hidden within this W in, and you feed the input, and depending on the input, the pattern will be retrieved from the key. And remember, this is element wise operation, in the sense like the first value of Xi will be multiplied with the first column of this matrix. The second value will be multiplied with the second column of the matrix, and so on and so forth. I'll break it down to this level later on. I'll break it down to this to the element wise level. So this is called key value memory retrieval. I have not discussed about value so far. I have only said the key part. So we basically extract the key from W in depending on X, right? So, and then we pass it through nonlinearity G. When we pass it through a nonlinearity, it will produce another vector, isn't it? It will produce a vector of size df, right? This will produce a vector of size df. I already told you. So a pattern of size df will be retrieved from W in. This is the key, and that key will be now plugged in, or that key will be applied to W out. You can think of W out as value storer. Okay, W out would look like this. This is W out. The dimension is df times d, meaning there are df number of values. Okay, you apply this matrix, this vector, that you obtain after this activation, to the value matrix, W out matrix, and this will produce some value, as if we are retrieving a row from W out, which will be upweighted by this vector 1 cross df, because ultimately is multiplication, right? Upweighted or downweighted, whatever. Let me draw this here. Okay, whatever I said. So this is my W in. In W in, there are these columns. Okay, there are these columns, and you apply xi mid here. Okay, it will produce a vector of size df. Okay, this will be passed through G. This will produce another vector of size df, and you have this value matrix W out. Okay, you multiply this with this, it will basically produce a vector of size t. Now these are all element wise operations, remember this, right? These are all elements. These are elements here, right? Okay, so each of these elements will be called as neuron. Essentially the values in W out will be upweighted by each of the neuron activations. These are neuron activations. Now if you break it down, if you break the entire computation into neuron level activation, it would look like this. So feed forward network, right, at the lth layer, the input is x. What is input? Xi mid at lth layer, right? It would look like this. U equals to 1 to df. What is df? Df is the dimension of the intermediate layer, right? Gu xi mid L, W in is the matrix, and U is the corresponding column, right? And W out L U. Now ultimately after this activation GU, we will produce a vector of size df. That's what I said, right? Df. So for each of these elements, I am looking at each of these elements by U. For each of these elements, right? How do we get each of these elements? Now xi mid L, the dimension is 1 times d. W in is d times df, and I am only interested in the uth index of it. So the dimension is going to be d cross 1, and this is the column, right? So df cross 1 or 1 cross df, doesn't matter because this is ultimately a vector. So this is the feed forward layer operation. You can think of this operation, this entire operation you denote it by NUL. Okay, this is called neuron activation. This is essentially here, these elements, isn't it? So NUL is a scalar. So NL is a DF dimensional vector. Is called a vector of neuron activation. Now these operations will be executed at every layer. Okay, now think of the last layer where we actually obtain the final output. Okay, for the last layer from where we get the output, the lth layer, the last layer, what is the input? The input is XNL, right? Because x1 x2 dot 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 xn, right? We have all these layers, right? We have all these layers, and let's say this is the last layer, lth layer, and the corresponding output that we obtain from this, for this xn, right? This will be fed to the unembedding layer wu, right? And this vector is denoted by xnl. Okay, so the final output fx, the distribution that we obtain, is essentially xn times wu, unembedding layer. Since this is a residual stream view, all these operations that we have done so far are additive, right? So what we have done so far, for every layer L, we have done this addition. Each number of heads have been added, right? And we did it for L number of layers. These are all additive operations, right? So for every layer we have added H heads, already discussed, right? What are the other elements that have been added? We also added L number of feed forward outputs, right? And xn was the original input that also has been added to this residual stream, right? So xln, this is nothing but this, right? And this will be multiplied with the unembedding matrix wn, the wu. Okay, all right. Now of course you can multiply wu with each of these things separately. So if you look at the final equation, you see that you can actually segregate the attention part and the feed forward part. This is the attention part, this is the feed forward part. Let me tell you why this is needed. Okay, now think of a basic neural network, a basic transformer without any feed forward network. Assume that there are two layers. Okay, assume that there are two layers, and at layer 1, right, at layer 1, this is the stream, right? Input is x, only one token, two layers, no feed forward network, only attention. Okay, so after the first layer you have this attention here. After the first layer, the output is x plus, and also let's make this thing even simpler. I already mentioned there are two circuits. One is query key circuit, other is output value circuit. The output value circuit is responsible for writing things to the residual stream. Let us ignore query key circuit for the time being, again making this thing simple. So essentially we have only done one operation, which is this output value operation, right, at the first layer for the input x, right? And let's call it as x1. So this is x1. X1 is nothing but there is this WOV. It went through this WOV1 and it produced x1. Okay, Similarly, you have another OV circuit, right? W2 OV. So, and that will produce the final output F, right? So F of X is X1 plus WOV2 X1. Clear? X1 is here. I have passed this thing through WOV2. Okay, it will produce this one. Clear? Right? So this is my final output after 2 layers with only OV circuit without feed forward network. Now let us expand this. So I replace X1 by this, X plus WOV1 X plus WOV2 X plus WOV1 X, right, which is X plus WOV1 X 1X plus WOV2 X plus WOV1 WOV2 X. So this will be multiplied with WU. So X WU plus WOV X WOV1 WU X WOV2 WU X WOV1 WOV2 WU. Okay, so if you look at this individual operations, right, what I have done so far, this is the residual stream, this is X, there is this WOV1, right, there is this WOV2, right, and then WU. Look at the first component. What is this? This is just XWU. Input has been multiplied with the unembedding layer. What is the second component? The second component is input. This has gone through WOV1 and then WU. What is the third one? Input. This has not gone through this. This has gone through WOV2 and then WU. Right? What is the fourth one? Fourth one is X, which has gone through W1, then W2, then WU. There are basically 4 circuits that you can think of. 4 effective circuits. For this one, the circuit would look like this: X, WU. For this one, this will be X, WOV1, then WU. For this, X, WOV2, WU. For this, WOV1, WOV2, U. Okay, so these has different, so these components have different names. The first component is this one, X times WU, and this is called the direct path. From X, you have a direct path to the output through unembedding. This one and this one, these are called full OV circuit, full output value circuit, because for each of these one, you just need one OV circuit, right? For this one, you have this OV circuit. For this one, you have this output value circuit, right? The third one is very interesting. I mean, the middle one. Here, you see, you can think of this OV1, OV2 multiplication of 2 matrices, two circuits as a single attention head, right? Because this is ultimately a matrix multiplication, and this is called virtual attention head, because you can think of a single virtual attention which encompasses both the attentions, right? So you can replace this. By another virtual, something like OV12, So direct path, full OV circuits, and virtual attention head. This is also called, this virtual attention is also called V-composition. These are all fancy terms. Okay. Now, why do we need all these things? Why do we need to decompose an attention into so many components? Because this will help you understand the inner working of transformer better, right? We'll look into each of these circuits separately, and we will explain how a transformer model works. Okay, and it will also give you a localized view of the transformer model. We have seen we essentially segregated the feed forward part from the attention part, which would not have been possible if you had used the traditional transformer, the traditional way of describing a transformer. Okay, we stop this. We stop here. Next lecture, we will discuss the interpretability of the transformer model with the help of the concepts that we discussed today. Thank you.